Welcome to the Explainer. Today we're diving into a really fascinating paradox in modern automotive engineering. We spent the better part of the last decade celebrating the electric vehicle revolution, mostly because it practically eliminates exhaust emissions. But as we fix what's coming out of the tailpipe, a completely new, hidden villain is emerging from the vehicles themselves, right under our noses, or well, right behind our wheels. We're talking about brake dust. Because as it turns out, the way we stop our cars might actually be just as important to our air quality as the way we power them.
Okay, let's dive straight into this, because honestly, this number is just staggering. Brake wear now contributes to roughly 1/3 of all non-exhaust particulate matter emissions. As tailpipe regulations have gotten incredibly strict, these non-exhaust emissions, meaning the particles shedding from tires, roads, and brakes, have actually surpassed exhaust emissions. It's wild to think about, but every single time you press that brake pedal, microscopic fragments of metal and friction material are literally being sheared off and launched right into the air.
And look, we're not just talking about having to scrub dirty rims on the weekend. We're talking about serious, tangible health risks here. This airborne dust is categorized by size: PM10, PM2.5, and the incredibly tiny PM1. To put that into perspective for you, PM1 particles are so small they can penetrate deep into your lungs and literally cross over into your bloodstream. Once they're in there, these ultrafine metal particles can increase heart rate variability and trigger inflammatory responses, the slightly larger PM2.5 deposits in the lungs, potentially inhibiting lung function over time. So this is a microscopic airborne enemy, and it's something we desperately need to engineer our way out of.
Section 1. The hidden brake dust problem.
Now, because electric vehicles are often a lot heavier than gas cars, this unseen enemy is rapidly outpacing tailpipe emissions. And for decades, the absolute, undisputed king of the brake rotor has been gray cast iron. I mean, it's cheap, it handles high heat really well, and it's super easy to manufacture. But its poor wear resistance? That's suddenly become a massive liability. Why? Because the impending Euro 7 regulations are dropping the hammer. Starting in 2026, incredibly strict limits on brake particulate matter will be enforced for new internal combustion vehicles. And by 2030, those limits get even stricter for EVs. So old, reliable gray cast iron simply cannot survive this regulatory shift. It just sheds way too much dust.
Section 2. Meets the high-tech contenders.
So how do we actually fix this? Well, enter the material scientists. They've essentially been working like detectives, hunting down some new sci-fi-sounding hero to coat our brakes and defeat this dust villain. Just look at the sheer topographical difference before and after treatment on these 3D microscopic profiles. On one side, you've got the archaic, super rough machining marks of standard gray cast iron. But on the other, you're looking at a futuristic, precision-coated surface. The base iron itself hasn't changed, but it's been armed with this incredibly resilient shield.
And this shield is created through a wildly cool process called extreme high-speed laser cladding, or EHLA. I know, it sounds like something straight off a spaceship, but here's how this chemical armor actually works. First up, a high-powered laser rapidly melts a base layer of 430L stainless steel right onto the iron. Then it adds a top coat that mixes that same steel with titanium carbide, which is an incredibly hard ceramic. The crazy part? Both of these layers combined are only about 100 microns thick. That is roughly the width of a single human hair. Yet this micro-thin layer is enough to drastically prevent the metallic breakdown that causes all that dangerous brake dust.
But hey, what if we just ditch the heavy cast iron altogether? That brings us to our second contender, plasma electrolytic oxidation, or PEO, applied to aluminum. Instead of shooting lasers, PEO uses high voltage in a liquid bath. Think of it as an extreme, souped-up version of anodizing. It creates a super hard alumina coating directly onto the aluminum surface. You can actually see the distinct, almost moon-like cratered surface it creates, especially on the cast aluminum compared to the somewhat smoother wrought aluminum.
So why go through all this trouble just to use aluminum? Simple. It is incredibly lightweight. Swapping out iron for aluminum brake rotors can reduce a vehicle's unsprung mass by roughly 20 kilograms. That is absolutely huge for vehicle dynamics and overall efficiency. Historically, aluminum would literally just melt or tear itself apart under the extreme friction and heat of braking, but this PEO treatment completely solves that vulnerability. Plus, shedding that much vehicle weight actually reduces other non-exhaust emissions too, like tire wear, just because the car is fundamentally lighter on its feet.
Section 3. Shrinking the brake test.
Now, you might be wondering, how do you accurately test the airborne emissions of these futuristic brakes without building hundreds of full-sized rotors and just repeatedly crashing test cars? The answer is brilliantly simple in theory. You shrink it. What you're seeing is a small-scale tribometer test rig developed by researchers to solve exactly this problem. Notice the completely sealed duct system encasing the testing unit. That ensures only clean, HEPA-filtered air enters the chamber. Then, as the mini brake pad grinds against the mini disc, all that microscopic wear debris gets whisked away into a cascade impactor. It acts basically like a high-tech vacuum that captures and perfectly sorts the microscopic villain by size.
But to make this data actually valid for a real car, the physics have to translate perfectly. The researchers use this really clever shrink and grow analogy, governed by one strict rule: constant energy density. By perfectly balancing the ratio of the pad area to the disc area and really carefully scaling the forces involved, a tiny 95mm test disc behaves thermodynamically exactly like a massive 350mm passenger vehicle rotor. It's genius.
So let's look at how this translates into the actual testing cycle. They run what's known as a WLTP braking simulation. And this isn't just mindlessly spinning a disc for hours. It's a fascinating, precisely computer-controlled dance that executes 303 completely unique braking sequences. For every single stop, the computer waits for the precise starting temperature, spins up to the exact target speed, applies a specific friction force, matches a designated deceleration rate, and then finally releases. It perfectly mimics the real-world driving of a car navigating everyday city streets and highways.
Section 4. Friction and wear results. All right, before we talk emissions, we've got to address the elephant in the room. Do these futuristic, super hard coatings actually have enough friction to stop a 2-ton car safely? The answer is yes, they absolutely do. Take a look at the coefficient of friction, or COF, across the tested materials here. A standard uncoated cast iron brake hovers right around 0.50. The laser-clad iron matches it perfectly. The cast aluminum is just a hair under. But check out the PEO-treated wrought aluminum at the bottom. It impressively outperforms the standard iron with a coefficient of roughly 0.65. It grips incredibly well. So safety, check. Then, we look at the physical mass lost from the rotors after these grueling tests, and wow, we see our first massive victory. The gravimetric mass loss, which just means how much physical material wore away from the coated rotors, dropped dramatically by a factor of at least 10 compared to the uncoated iron. The laser cladding and the PEO alumina are so tough that these new discs are practically immortal compared to the stuff we bolt onto our cars today.
Section 5. Passing the Euro 7 test.
All right, now for the final boss level. We're scaling this data back up from the tiny test rig to a full-sized passenger vehicle to see if it actually survives the ruthless Euro 7 regulations. Because the wear resistance of these materials was so extreme, it directly translated into crushing the airborne particulate matter emissions across the board. The laser-clad iron saw a 73% reduction in PM10 dust. The wrought PEO aluminum hit a massive 75% reduction. Even the cast PEO aluminum saw a 60% drop. As the researchers noted, it's pretty simple. If you stop the physical wear, you stop the dust. It's a direct, undeniable correlation.
And this brilliantly illustrates the climax of the entire study. Look at the extrapolated whole vehicle PM10 emissions. That towering bar you're seeing for uncoated cast iron, it fails spectacularly at over 31 milligrams per kilometer. But then look at the laser-clad iron and wrought aluminum. Our coated heroes drop all the way down to roughly 8 milligrams per kilometer. That is a monumental collapse in pollution.
But, the scientific battle isn't entirely over just yet, because the Euro 7 limit for gas and hybrid cars is actually 7 milligrams per kilometer. Now, at 8 milligrams, these new coatings are a monumental leap, and with some slight brake pad optimizations, they're going to easily pass that icy limit. But look at the electric vehicle limit, 3 milligrams per kilometer. No way around it, EVs are heavier, and regulators are demanding near perfection from their brakes. Even with space-age laser clouding and plasma oxidation, hitting that incredibly strict EV target is going to require even more engineering wizardry.
Which really leaves us with this provocative thought. We so often call EVs zero-emission vehicles. But as we completely eliminate the exhaust from the tailpipe, the actual physical wear and tear of the vehicle moving through the world becomes our greatest environmental hurdle. Are we ready to redefine what a truly clean car means in the modern era? What this study ultimately proves is that the future of green transportation isn't just hidden inside the battery pack, it relies heavily on the brilliant material scientists figuring out how to stop us safely without leaving a trace of dust behind. Thanks so much for joining me on this explainer, and as always, keep questioning the world around you.